Hello there, this is a geometry video. It is chapter 5, section 2, and today we are continuing with some points of concurrency. I mentioned in our last video, we talked about the circumcenter and the incenter, which is the point of concurrency of the perpendicular bisectors and the angle bisectors respectively. And today we are going to be talking about two more points of concurrency, and the first is medians and the second is altitude. So let us begin with the medians. First and foremost, we need to make sure that we define what a median actually is. And so that's what we got here first going on. A median of a triangle, not to be confused with a mid-segment. If you recall, a mid-segment connects two midpoints to each other. So in this case, you're not connecting, D is the midpoint of AB, but C is not the midpoint of any of the segments. So you're not connecting midpoints. But it is a segment, and the endpoints of this segment are a vertex. So you'll see here we're using vertex C, and then the midpoint of the opposite side, so you would go to point D, and that's what we'll refer to as the median. So as the diagram suggests, we know that it's the midpoint because these are marked congruent. So CD, segment CD, is the median of triangle ABC. Now every triangle has three medians. You could connect vertex B to the midpoint of AC, and you could connect vertex A to the midpoint of segment BC. So every triangle has three medians, and as we said in the previous section, all of the medians are concurrent, meaning they all cross in one point. And so the point of concurrency of the medians of a triangle is called the centroid. All right, and it's actually quite interesting. A centroid of a triangle, the point that we refer to as the center of a triangle, is actually the place where you achieve perfect balance of a triangular shape. It's actually pretty cool. So I don't know if you've seen that you can balance anything that's in a triangular shape, and if you find the centroid, if you put a point, like if it's like a flat sheet or whatever, and you put it on top of that point, it will perfectly balance there. It's the center of gravity. It's really cool. But anywho, we have a theorem about the centroid, and so here's our theorem. It says the medians of a triangle intersect at a point called the centroid, and this point is 2/3 of the distance from each vertex to the midpoint of the opposite side. Now that might sound kind of like crazy, so hopefully the diagram will make more sense. It is kind of cluttered, if you will, because if you look at this guy, it only has one of the medians at a time. But when we put all three of them in the diagram that we have down here, it can get kind of crazy. But you can tell that point J is the midpoint because of AB, because these two segments are marked congruent. You can see that point K is the midpoint of BC because they're both marked congruent. And you can tell that L is the midpoint of AC, again, because these two are marked congruent. And so we're just connecting each vertex with the midpoint of the opposite side. And when you do that, they all cross at this point P. And you'll notice that when you do that, you can look at each median, and you can kind of see that it's divided into two pieces. There's the JP to PC, there's KP to PA, and then there's BP and PL. So each of those medians is cut up into two pieces. And so basically what the theorem is telling us is that the point P divides the median into a 1/3, 2/3 ratio. So basically the distance AP, which is the longer of the two, this is clearly you can tell this is the shorter piece, the longer piece. So AP is 2/3 of the entire segment. So basically if AP is 2/3, then that only leaves 1/3 for PK. So again, that happens for all the medians. So then you also have that BP is 2/3 of BL, and then CP, the longer part, is 2/3 of C all the way to J. So what that basically means is that if this entire segment was, I don't know, let's say it was 9, then you would break it up into threes because you have 3, 6, 9. And so 1/3 of 9 is 3, and 2/3 of 9 is 6. So JP would be 3, and CP would be 6, and the whole thing would be 9. So that's kind of how that works. And again, it is the center of gravity. It's kind of cool. So that's the theorem. And we are now going to go to our example, hopefully, if my pen will allow me here. Not sure why it wants me to cap my stylus. I'm using it. Let's wait for it to really apologize. Okay. I capped it. Now I'm reopening it. Okay, I'm not sure what's going on. And now it decided to work, and now it's advanced 5,000 pages. Okay. Let's see if I can get back to where I was. Hello. I really apologize for this inconvenience and hope that I can all right, here's our example. I'm not exactly sure what just happened there, but at least everything still seems to be here. Now if I could just get my pen to work, it would be awesome. I took my battery out to reset it, and I think I put the battery back in wrong. I think we're good to go now. There we go. Sorry about that. Okay, so it says here, in triangle ABC, point Q is the centroid, and they're telling us that from B to E, this entire segment is 9, and go figure, I just gave you an example of 9, and they want us to find BQ and QE. So I'm going to do that, and I'm going to show you a couple of ways that that you can figure this out, okay? So probably some of you already know what the answer is, but I also want to do it algebraically so that those of you that are going to struggle a little more will know how to do it. So basically BQ, if we look at the diagram, BQ is the larger of the two pieces. So BQ is equal to 2/3 of QE. And we know that, sorry, not 2/3 of QE, it's 2/3 of BE. And they told us that BE is 9, so we're going to go ahead and put 2/3 times 9 in there, and then 2 times 9 is 18, and 18 divided by 3 is 6. So we get 6 as our answer for BQ. And then they want us to also find QE. So QE is only 1/3 of BE. And so QE would be 1/3 of 9, or just 3. So that's how you could do that algebraically if you want, but a lot of you could probably just do that in your head. So now we're going to use the same diagram, but this time they're telling us that the segment F to C is equal to 15, and they want you to find FQ and QC. Okay, so here we have another example. Again, we're dealing with a centroid, and it states in triangle JKL, PT, so this segment right here, PT, is equal to 2. They want us to find KP. All right, so first thing we have to do is make sure that point P is actually the centroid, and it is. because you can see that each of these medians is going from a vertex to the midpoint of the opposite side, and you know that R, S, and T are the midpoints because all of these segments are marked congruent. So now that we know that it's actually the centroid, we can go ahead and say that KP is equal to 2/3. Now again, KP is the longer of the pieces, so KP is 2/3 of the whole, which is from K to T. All right, and then PT, so what we can do now is kind of do some distributive property. Again, some of you might have already been able to do this in your head, but I want to show you how you can do it with some algebra in case you can't do it in your head. So KT is basically made up of these two pieces, KP plus PT. KP plus PT. Okay? And we know that PT is 2. So we're just going to basically solve an algebraic equation here. And so I'm going to get 2/3 KP, I'm distributing, 2/3 times KP, and then 2/3 times 2, which is 4/3. And that equals KP. Now KP is my variable, that's what I'm trying to find. So what I need to do is move these KPs to the other side. So what I'm going to have is 1 KP, which was already on the left, and then I'm going to subtract 2/3 KP, so that the KPs are on the same side, and it's going to equal 4/3 on the right, because the 4/3 is going to stay there. So now basically we have is 1 minus 2/3, and 1 is the same thing as 3/3. So 3 minus 2 is 1/3, so now what we have is 1/3 KP equal to 4/3. And our last step is to times both sides by 3, so KP equals 4. And that's how you can use algebra to do that if you don't want to do it in your head. So now you can try to do it yourself, number 2, and then we will move on to our next example, dealing with the centroid. Now in your book, this is actually an example about an artist, a performance artist, who balances triangular pieces on these sticks. And so they're basically asking us to take those triangles that she has and basically find the point where she balances them, because again, as I said earlier, the centroid is the center of gravity, so if she manages to put the triangle directly on that point, on that centroid, then the triangle will perfectly balance. But again, if you want to read up on the story, you can look at the example in the textbook. I didn't want to write out all of the story, so I've just put up here the core pieces of information. The vertices of the triangle, which were given, and so I'm looking for the centroid now. So what I've done is I've already graphed point 1, 10, 5, 0, and 9, 5. So this is my triangle, and I need to find the centroid. And so what I'm going to do is, I know that the centroid is going to go from a vertex to the midpoint of the opposite side. So I'm going to go ahead and kind of give my points letters so that I can refer to them. So we'll call this point A, and we'll call this point B, and then we'll call this point C. And so what I want to do right now is I want to find the midpoint of side AB. You know, it doesn't matter which side you start with, but I want to find the midpoint of side AB and then connect it to point C. So side AB, if you remember how to find the midpoint, I'm going to call the midpoint point D, but the way that you find the midpoint is by taking the x-coordinates of A and B. So this is my A, 110, and B was 50, and C is 95, okay? So I'm going to take the x-coordinates of A and B, which is 5 and 1, and divide by 2. Take the x-coordinates of the y-coordinates of A and B, 10 and 0, and divide by 2. So now I get 6 divided by 2 is 3, and 10 divided by 2 is 5. So the point 1, 2, 3, 1, 2, 3, 4, 5 is right about here. And since this is 3, 5, and point C is 9, 5, they have the same y-coordinate, which tells me that this segment is a horizontal segment. So what I'm going to do next is I'm going to actually count how far apart they are. This x-coordinate is 3 and this x-coordinate is 9. So 9 minus 3 is 6. So that tells me that CD equals 6. And we know that the centroid is going to be a 1/3, 2/3 ratio. So if we take 6 and divide it by 3, you're going to get each piece is going to be 2. So the 1/3 is going to be 2 and the 2/3 is going to be 4. So if you count over from point D 2 units, you're going to be right here at 5. So the x-coordinate will be 5 and the y-coordinate will be 5. So we are claiming that the centroid is 5, 5. Now we can check that because of course that we've only found one so far. You should at least check 2 of them, so or at least check it with one other one. So we can also go ahead and find point F if we want, or it doesn't really matter. We can find BC. Let's try to find the midpoint of BC. So I'm going to call that point F. And again, what I want to do is I want to find another median and see if it's going to go through the same point, okay? So we're going to start with vertex A, and I want to find the midpoint of BC. So I'm going to use now point B and C. So 5 plus 9 divided by 2, and 0 plus 5 divided by 2. So we're going to get that F is 9 plus 5 is 14 divided by 2 is 7, and 5 divided by 2 is 2.5. So we're going to get 7, 2.5. So here's 5, 6, 7, and then 1, 2.5. And it's roughly right about here. And when I graph that, you can see that it goes nicely right there. Another thing that you can check is also to do B to AC. So let's see, we've got D, we call this F. Let's go ahead and call the last one E. So for E, we're going to find the midpoint of AC. So we want to go from point A, so the x-coordinate is 1, point C is 9 divided by 2. X-coordinate of A is 10. X-coordinate of C is 5 divided by 2. So then like 10 divided by 2 is 5, and 15 divided by 2 is 7.5. So E is 5, 7.5. So 5, 7.5 is right about here. And then what you see there is that this guy is actually a vertical line, so you can actually count here as well to confirm again that this is in fact the centroid. So again, what are the coordinates of the centroid? 5, 5. And we've double checked it with all the other segments as well. Now you don't have to check it twice, but it is a good idea to at least check one of them. Okay? So now we're going to do a second triangle with different vertices, and so you need to graph the triangle first, and then do the same thing we did earlier to find the coordinates of the centroid. All right, and so then we move on to the next point of concurrency, and that is of the altitudes. And with the altitudes, the altitude of a triangle is the segment that goes from a vertex of the triangle, like point B, for example, and it has to be perpendicular, that's important, it has to be perpendicular to the line containing the opposite side. And the reason why they say that, why they say to the line and not just say to the opposite side, is because sometimes you have to extend the line because this altitude can be inside the triangle like it is in the first diagram, it can be outside the triangle like it is in the second diagram, or it can be on the triangle as it is in the third diagram. So I know what you're thinking. The altitude is basically the height of the triangle. And so in this case, the height is inside the triangle because it's acute. But in this case, you have an obtuse triangle. And if I try to find the altitude of this triangle, I actually have to extend the side AC so that I can actually find that height. And then of course if you have a right triangle, then the height is actually on top of one of the legs of the triangle. So just so that you're aware, the altitude could be inside, outside, or on the triangle. So BD right here, and in the first two diagrams it's BD. BD is an altitude from B to AC. Every triangle has 3 altitudes. Just think of it as, what if I rotated the triangle and made the other side the base? Then that would be the height. So every triangle has 3 altitudes. And then of course the last diagram says BA is actually a side of the triangle, but it also is the altitude from B to AC. So there we go. The point of concurrency of the altitudes, we don't have an orthocenter theorem like we did in the other 3 cases, but they are concurrent. So the point of concurrency of all the altitudes of the triangle is called the orthocenter. So now we have circumcenter, which is the perpendicular bisectors. We have the incenter, which is the angle bisectors. We have the centroid, which is the medians, and then we have the orthocenter, which is the altitudes. And so I have a diagram here for you just to show you how the obvious height is the B to G, but if I made BC the base, then the perpendicular distance from this side to the opposite vertex is AF. And if I make if I make AB the base of the triangle, then the height or altitude of the triangle would be from vertex C to the opposite perpendicular, which would be here. So when those altitudes all get drawn in, then you end up with your orthocenter. Alrighty? So what we're going to do now is our last example. And in this example, we don't have a theorem about the distances and stuff, so we're just going to try to find the points or the coordinates of the orthocenter. So here I have a triangle, and I didn't put the vertices here, so we've got -2, 4 is F, and 4, 4 is G, and 1, -2 is H. So there are my vertices. Find the coordinates of the orthocenter. Now, believe it or not, what you want to do is find the altitude, and since F and G both have the same y coordinate, this is actually a horizontal line, and so finding the perpendicular is going to be really easy, because from -2, from here to here is 2 points, so this is -2, -1, and 0, so you have 2 units there, and then from 0 to 4 is 4 units, so you have a total of 6 units. So halfway is going to be 3, and the altitude is just going to be right down the middle. Just like that. Okay? But we need to know where that intersects with something else. But what I want to do right now is, I'm not convinced that you're going to get a triangle as easy as this one in the do-it-yourself or on the homework. So I'm going to actually do this the longer way, because my guess is that you're going to have to do it that way when you get to your example. So instead of using the easy segment, which is the horizontal segment, I'm actually going to use the not horizontal segments to show you how this is supposed to work. So let's take that guy off, and then let's do it the long way. So basically what we have to do is we have to find a line that goes from a vertex like F, and it has to be perpendicular to the other side. So the first thing I want to do is find the slope of HG, and you can find the slope of HG very quickly by looking at your graph, or you can do the slope formula. But here's point H and here's point G, so if I went, how many units do I have to go up and how many units do I have to go over? It looks like I'm going up 2 over 1. So I think my slope is, my slope for HG is actually 2. Now if you're not convinced about that, you can actually take point G and H and calculate the slope yourself. You can go y2 minus y1 over x2 minus x1. And -2 minus 4 is -6, and 1 minus 4 is -3, and -6 divided by -3 is in fact +2. So whether you choose to do it with the slope formula or just by looking at the graph, the slope is 2. But what I want is a slope that is perpendicular to this, right? I want the line to be perpendicular. So my slope is going to have to be -1/2. Okay, so I know what my slope is. I have a point F, which is -2, 4. So now I find the equation of the line by going y minus y1 equals m times x minus x1, and then simplifying that. So I get y minus 4 equals -1/2 x, and then -1/2 times 2 is just -1. And then we're going to add 4. So I get that y equals -1/2 x plus 3. This is one of my equations. Okay, so 1, 2, 3, down 1. Over 2. So my line's going to look like that. Okay? That's my perpendicular line going from F to the opposite side. Now I have to do this again because I'm going to do it to this side from FH to G, also draw another one and see where they cross so that I can get my answer. Okay, so I have to do this process all over again. So this time, I want the slope of FH. And again, you can use the slope formula, or you can just count. This looks like it's going to go down 2 over 1. Looks like it's -2. And then I want the perpendicular slope. And if this slope is -2, I'm going to flip it over and make it opposite sign. So it'll be +1/2. That's my slope. And the point that I'm going to be using is point G, which is 4, 4. And so here we go again. We're going to go y minus y1 equals m times x minus x1. I'm sorry for the crampedness here. Don't have a lot of space. Y minus 4 equals 1/2 x, so 1/2 times x, 1/2 times -4 is -2. Then we're going to add 4 to both sides. So I'm going to end up with y equals 1/2 x plus 2. There's my second equation. So there's going to be my plus 2. And 1/2 is up 1 over 2. And it's going to go just like that. Okay? And there's my perpendicular segment there. So that's my altitude. And what I'm trying to figure out is where those two lines cross. Well, lucky for us, we can actually use an algebra method of substitution to find where they cross, because it looks like it's 1 and 2.5, but we can't be sure of that just yet, so we want to confirm that algebraically. So what we do is we make the two equations that we just got and we make them equal each other. We take the 1/2 x plus 2 and have it equal the -1/2 x plus 3. So I put the x's on the same side, so I'm going to add a 1/2 x to each side. Subtract this 2 from both sides, and 1/2 and 1/2 is 2/2, or just 1x. And then they cancel, and 3 minus 2 is 1, so x equals 1, which was what we thought. It was 1 and 2.5. So now what we got to do is find the y coordinate by plugging it into either one of those equations. So y is equal to 1/2 x plus 2. I'm plugging it into this equation right here. And then I'm going to replace the 1, because this is x equals 1. And then we get 1/2 plus 2. And 2 is the same thing as 4/2. So 4/2 plus 1/2 is, in fact, 5/2. So y equals 5/2. And so our solution the coordinates of the orthocenter are x equals 1 and y equals 5 hat.